How about we adjust the telescope to observe universes being formed? And goodness, who all requested this. We're tracking down cosmic systems in the depths of time. However long, scientific inquiry has delved into the origins of our universe. The primary explanation has been the theory of the universe's genesis. Numerous studies and the collaborative efforts of countless researchers have bolstered this hypothesis, providing significant evidence for how the universe came into existence. However, the landscape of science today is remarkably different from that of the past. Technological advancements consistently introduce new theories and perspectives, challenging what we once believed about established knowledge. In this evolving scientific landscape, where new discoveries reshape our understanding of the universe, Neil deGrasse Tyson has emerged as a prominent voice. Now, a significant breakthrough has been revealed as the James Webb Space Telescope has unveiled a finding that casts doubt on the well-established theory of the universe's genesis. This discovery includes the identification of an astonishing 750 new worlds, each of which defies our previous assumptions about what planets should resemble. By the way, the James Webb Space Telescope was designed to help us understand the origins of cosmic systems, so we shouldn't be surprised that it leads us to ponder our understanding. Join us as we explore how the new images from the JWST challenge the theory of prehistoric cosmic explosion. With the discovery of 750 new systems, researchers have advanced the theory of prehistoric cosmic explosion as the primary explanation for the origin of our vast universe. According to this hypothesis, around billions of years ago, the universe emerged through a peculiar grand event of some sort. It's the ultimate birth narrative of the universe. The extraordinary concept of the images captured by the James Webb Space Telescope has tested researchers' understanding of the universe's beginnings. The theory that these images directly contradict is the Big Bang theory, which has long been regarded as an undeniable truth by most cosmological scholars. These systems appear to be too small, too smooth, too old, and too varied when compared to the expectations of the Big Bang theory. The small size of the observed systems fundamentally contradicts the expected behavior in a growing universe, as indicated by the theory. As the universe expands, objects should seem larger with increasing distance. According to the theory of the universe's origin, at the beginning of the universe, all matter, energy, and the building blocks of the cosmos were compressed into an incredibly tiny and highly concentrated point. This point is known as a singularity. Within the singularity, all the matter and energy in the universe existed in an extremely dense structure. The extreme density implies that an immense amount of mass and energy was concentrated within an imperceptibly small space. The temperature within the singularity would exceed any temperature that can be observed or replicated in our current understanding of the universe. The energy stored within this hot, dense point was the seed from which the entire universe would unfold. Expansion. That's why the singularity marked the beginning of the universe as we know it. It was the origin from which everything in our universe emerged. After the initial singularity, the universe commenced its journey of evolution and expansion. This process occurred over approximately 13.7 billion years, shaping the universe as we know it today. The expansion of the universe began with a remarkable explosion of rapid expansion known as inflation. During this stage, the universe expanded at an incredible rate, far surpassing the speed of light. It's as if the fabric of space itself was stretching and expanding, engulfing everything within it, curious to see what would happen. Inflation played a significant role in forming the large-scale structure of the universe. It smoothed out irregularities, homogenized the distribution of matter and energy, and set the stage for the subsequent development of galaxies, stars, and other massive structures. As the universe continued to expand, the rate of growth gradually slowed. Yet, with this information, it's important to note that, although the initial period of inflation ended, the universe continued to expand at a measurable rate. This ongoing growth is referred to as the expansion of the universe or cosmic expansion. Researchers have observed the effects of this expansion through various observations, such as the redshift of light from distant galaxies. The redshift indicates that as the universe expands, light waves are stretched and shifted towards longer wavelengths, moving them towards the red end of the spectrum. We'll delve into the details of this later in the video. At first glance, the images of the new galaxies taken by the JWST look absolutely stunning. Undoubtedly, you can see numerous galaxies all in the same frame, and the sheer power in the photographs is something you simply can't overlook. Yet, that is how things appear to the average person. For scientists, the situation is the opposite. These images are astonishing to say the least. They don't match what researchers thought they would see based on their hypothesis. They are observing far more galaxies than expected, and these galaxies differ in several remarkable ways. They are smoother, smaller than anticipated, and truly ancient. These numerous surprises are causing quite a stir among the researchers. One paper even begins with the word alarm in its title, so you know things are serious. The galaxies appear to be something they shouldn't. The age of the observed galaxies seems extraordinarily unusual. Here, the JWST observations demonstrate the existence of worlds that appear unexpectedly old. This challenges the conventional timeline of galaxy formation and evolution within the framework of the theory of prehistoric cosmic explosion. Additionally, there is the reality that the quantity of detected galaxies far exceeds the expectations set by the Big Bang theory. A specific distribution and concentration of galaxies are based on the expansion and progression of the universe. However, the images from the JWST showcase an immense number of galaxies, which prompts inquiries regarding the reliability of the predictions made by the theory. It is also notable that the uniformity of these galaxies is completely unforeseen. The theory concerning the universe's inception suggests that galaxies should display irregularities and variations in their forms due to the dynamics of their formation and evolution. Yet, the JWST images reveal galaxies that appear intriguingly smooth, lacking the expected complexity and natural unevenness one would anticipate according to the Big Bang nucleosynthesis theory. While expansion was taking place, all the components that comprise our universe were confined to a minuscule volume. Clearly, matter could not endure in such a compact space, so something had to change. As the universe expanded and cooled, transformations occurred. Particles such as protons, neutrons, and electrons began to engage with light and energy in their environment. These interactions were crucial in shaping the development of matter in the universe. In the initial moments following the Big Bang, a process known as nucleosynthesis transpired. This process involved the creation of lightweight elements like hydrogen and helium. The extreme temperatures and energy during this phase allowed protons and neutrons to combine, forming these essential nuclear building blocks. Hydrogen, the simplest and most abundant element in the universe, was primarily created during this early period. Helium, the second most prevalent element, also emerged at this time. These elements were pivotal in facilitating the formation of stars, galaxies, and more complex elements that would appear later in cosmic history. The amalgamation of these fundamental elements marked a significant milestone in the universe's evolution. From an initial sea of particles and energy, the young universe transitioned into a state where matter began to manifest. This process laid the groundwork for the diverse array of matter and the vast cosmic structures that eventually came into existence. Presently, Big Bang researchers anticipated observing galaxies that were chaotic and mixed due to numerous collisions. However, the JWST images tell a different story. Instead of disordered and jagged galaxies, the images predominantly depict smooth disks and orderly spiral formations resembling the universe as we perceive it today. This unexpected finding challenges the assumption that mergers are a standard aspect of galaxy evolution, as it seems these newly observed galaxies haven't faced the trials one would typically expect under the Big Bang theory. If only a few or even no mergers are taking place, it becomes unlikely for small galaxies to evolve into significantly larger ones. This suggests that these galaxies were never originally small to begin with. Furthermore, the optical illusion anticipated by the expanding universe theory, where objects seem smaller with increased distance due to expansion, also doesn't hold true. As astrophysicists have carefully observed and charted the universe, they have uncovered a remarkable pattern: the clustering of galaxies and the overall architecture of the universe. Galaxies tend to group into enormous clusters, groups, and superclusters, forming intricate networks that span the cosmos. This observed large-scale structure aligns with the predictions set forth by the theory of the universe's origin. According to this hypothesis, The universe originated from an exceptionally dense and hot state, and over time it expanded and cooled. As the universe grew, gravity played a vital role in determining the distribution of matter and the formation of galaxies. The gravitational effects expected from the initial dense and expanding state posited by the theory align with what we observe today. Gravity pulls matter together, causing galaxies to cluster in specific regions and form filamentary structures that connect them. These configurations reveal the cosmic web-like nature of the universe. The presence of these galaxy clusters and the interconnected web of matter offers strong support for the Big Bang theory. The arrangement of galaxies and their distribution throughout the universe corresponds with the gravitational effects predicted from the initial dense and expanding state proposed by the hypothesis. Upon re-examining the size of the galaxies discovered by the James Webb Space Telescope, it becomes evident how the images portray a completely different reality from what we previously believed our universe to be. According to Big Bang researchers, these small galaxies evolve and advance into the larger galaxies we observe today through a process of interactions and mergers. To simplify this theoretical scenario, you can envision individual galaxies as a collection of stars and dark matter bound together by gravity. In this scenario, when two galaxies come into close proximity, their gravitational fields interact with one another, influencing the stars and gas within each galaxy. If these galaxies were to collide, the merger would lead to the formation of new stars and increase the size of the resulting galaxy. This merging process is referred to as cosmic nucleosynthesis, and as suggested by the theory of the primordial cosmic explosion, it is believed that these small galaxies would have undergone various mergers over billions of years to form the large spiral and elliptical galaxies we see today. However, the universe observed by the James Webb Space Telescope, JWST, contradicts this notion. The galaxies identified by the telescope are surprisingly small, smooth, and seemingly ancient, challenging the assumptions established by the theory of primordial cosmic explosion. The images captured by the JWST reveal a population of galaxies that are much smaller and smoother than anticipated, raising questions about the validity of current cosmological models. The origins and development of these galaxies appear to contradict the predictions made by the theory of the universe's origin, which asserts that galaxies should evolve through mergers and collisions over time, rather than the chaotic and unpredictable structures expected from cosmic mergers. The universe, as perceived through the JWST, displays distinct smooth forms indicative of modern structures.